This video is about the complex roots of polynomials. And in this video, I'm going to focus specifically on quadratics. So the first thing that I'd like you to think about is, what does a quadratic look like visually? What does its parabola look like if it has complex roots? And could you draw a sketch of an example? So here are two examples of quadratics where there are complex roots. And we've spoken before about how b squared minus 4ac is less than 0 in these cases. In this video, I'm going to focus specifically on quadratics written in the form az squared plus bz plus c equals 0, where a, b, and c are real numbers. So it's important to point out that I'm focusing on the case where the coefficients and the constant are all real. And interestingly, in this case, for this type of quadratic, when I find its complex roots, it's always the case that the complex roots, the two complex roots, are conjugates of each other. And this is called the conjugate roots theorem. Now, we've already looked at questions where, given the quadratic, we've had to use the minus b formula to find the roots. So I'm going to work on the basis that we know how to do that. And if you're a bit uncertain, go back and look at the previous video that dealt with that. In this video, I'm going to look at the scenario where you're given one of the roots of the quadratic and you want to possibly check to see if it actually is a root for definite and find the other root also. And I'm going to look at a couple of different ways in which we can do this. So my example is going to involve the quadratic z squared plus 4z plus 5 equals 0. And I want to show that minus 2 plus 1i is a root, and I want to write down the other root. So approach number one is just the approach that we've used previously when trying to find the roots of quadratics. It's just to use the minus b formula. So minus b plus or minus the square root of b squared minus 4ac all over 2a. Now, like I said, I've shown how to do this in a previous video, so I'm not going to go through all of that again. But what I would like you to do yourself is to make a note of your a, b, and c values for this quadratic, fill in the formula, and see what you get. You're going to expect that minus 2 plus 1i is one of the roots. And then, because of the conjugate roots theorem, I would expect the other root to be minus 2 minus 1i. And notice that this is the case because in this quadratic, the coefficients and the constant are 1, 4, and 5. So they are all real values. So take a moment, pause the video, work out your solutions to the minus b formula, and see if you get them correct. And following this approach, you find in fact that z is equal to minus 2 plus 1i, and the other root is minus 2 minus 1i. And that's what we expected to happen. We can see that these two roots are conjugates of one another. Approach number two is an approach that we're familiar with from previously in algebra. If I want to confirm that something is in fact the root of a function, well, then all I need to do is sub it in, and I should expect for the result to be equal to 0. So let's take z equals minus 2 plus 1i and sub it in for z that we see in the quadratic. And again, pause the video here, do that yourself, and see if it does in fact come out as the 0 that we expect. So I've replaced z with minus 2 plus 1i. I'm squaring out my first bracket, just be careful with that. I multiply out my second bracket and stick the plus 5 at the end. Now just a little bit of tidying up. So of course I see an I squared there, and I know to replace that with a minus 1. And on inspection then I can see that my real terms, when I put them together, 4 minus 1 is 3, minus 8 is minus 5, plus 5 is 0. So these all effectively cancel out. And minus 4i plus 4i is also 0. So this confirms that z is in fact a root. Now that I'm sure that minus 2 plus 1i is a root, I have direct access to the second root. And that is, of course, because the quadratic that I'm dealing with, z squared plus 4z plus 5 equals to 0, has real coefficients. So that means that once I know one of the roots, the other root must be the conjugate of that root. So in approach 2, we relied on the roots to figure out the solution. In approach 3, we're going to look at how roots and factors are related and use factors to work towards our solution. So I'm going to start by assuming that z equals minus 2 plus 1i is in fact a root. And if that's the case, then the other root, of course, would have to be its conjugate because of the nature of the quadratic with its real coefficients. And I'm then going to say, well, if these are the roots, I can figure out the factors of the quadratic. And of course, I simply do that by bringing this information on the right-hand side of the root equation over to the left. So if this is the case, then I've got two factors, z plus 2 minus 1i and z plus 2 plus 1i. And of course, I'd expect when I multiply the factors of my quadratic together that I would get the quadratic in question. So I'm going to do that and see what happens. Now, I find that when multiplying this out, because you've got 3 terms in each bracket, it gets a little bit clunky. So I actually really like to represent this using the array, and you'll see why in a moment. Just to say, if you're not familiar with the array or you don't like it, it's totally fine to multiply out as normal, but I'm going to use the array. So here's my array. If I'm correct, I'm expecting that when I multiply out, I should end up with that original quadratic z squared plus 4z plus 5. So I'm putting my terms from my brackets along each of the sides of the array, and then I'm going to multiply into it. At this point, pause the video, multiply it out yourself, and see what you get. And see, do you notice any nice kind of symmetries going on as you work through this multiplication? So here's my first row, and my second row, and my third row. And just a couple of observations here now. You'll see that, looking at this box here, the plus 1zi. On the other side, I've got minus 1zi. And they're going to cancel out. I've got plus 2i and minus 2i. And they're going to cancel out. I've got the I squared in the corner. And I'm going to have to replace that with minus 1. And just note this little cancelling pattern that occurs. That's always going to happen if you have created your factors from conjugate roots. So it's nice, it kind of tidies itself up in a way. You're also going to find that this information here is going to be a perfect square. That obviously then gets disrupted by this minus 1i squared in the corner. So nearly there. Just going to assemble it now. So my z squared is going to go first. My z terms are always going to be on this diagonal. And then I'm going to have my constant formed by this diagonal here. Of course, this doesn't look like it's real right now, but that minus 1 will go in and ensure that it actually is. And then last little step. And I've arrived at my quadratic. Now, you might think this is slightly overkill given the slightly shorter methods that we've seen up until now, but this is a particularly useful way to approach a question if you are told one of the roots, but you're not told the quadratic itself. So it's a nice way to build the quadratic if it's unknown to you initially. And then finally, I've got approach number 4. And approach number 4, we're again familiar with from previous algebra chapters. So there is a formula that you can use to create a quadratic if you know what its roots are. And that formula is z squared minus the sum of the roots times z plus the product of the roots. So again, I'm going to start this case by assuming that the root that I'm being given is correct, in which case my other root would have to be its conjugate. I'm going to build the quadratic. If I get z squared plus 4z plus 5 equals 0, then I'm satisfied that minus 2 plus 1i is a root. And of course, then I also have my other root, which is the conjugate. So it's simply a question of subbing in this case. So I first of all fill in the sum of the roots. Now notice sum means that I'm adding the roots together, and you might say to yourself, well, why is it a minus here? But I'm adding minus 2, so plus minus is a minus, and I'm adding minus 1, so that's going to be a plus by a minus is a minus as well, hence the negatives here. So a quadratic with these two particular roots would look like this, and then it's simply a question of tidying it up and seeing does it conform to expectations, ending up as z squared plus 4z plus 5. Well, I can see in that first bracket that I've got a plus 1i and a minus 1i, so they're going to hop off, and I'm going to have minus 4 left inside the bracket with a z. And then when I multiply out the two brackets at the end. Notice it's a difference of 2 squares, if you like. So you can say it's minus 2 squared minus 1 squared. Sorry, of course, that should have an I in it, shouldn't it? So minus 1i squared. And then it's simply going to be a matter of just multiplying that out. And I'm almost there now. All I have to do is replace my I squared. And I can see at this point quite clearly it's going to end up giving me, which confirms the fact that z equals minus 2 plus 1i is a root. And no matter which of these approaches you take, don't forget to conclude. We were asked to show that minus 2 plus 1i is a root, so we'd have to say that. And that's how that would look. Z equals minus 2 plus 1i is a root of our quadratic. And of course, we're asked to state our other root clearly. And the other root is z equals minus 2 minus 1i. Please don't feel that you need to take all 4 of these approaches. Obviously, given different circumstances, different ones will be more appropriate. The first approach that we looked at using the minus b formula is probably most appropriate if you're not given either of the roots. However, you can use it to confirm roots. Approach 2, where we're asked to just simply sub the root in and check if we get equal to 0, is a nice quick way of confirming a given root. Approach 3, where we used the factors to create the quadratic, is a really useful approach if you know the factors or the roots, but not the quadratic. And the same goes for approach number 4, using the formula minus the sum plus the product. Again, that's really useful if you know the roots, but not the quadratic. In any case, these approaches, all of them will work in the case where A, B, C,